Um, you will, I told you a couple of times, but eventually you will have one lesson at least on more sort of exciting topics in combustion, which is like the application of numerical combustions right now. So how are computers used to solve turbulent combustion problems, okay? So you're going to have that with Pasquale Lapena, who's collaborating with me. So eventually he's going to open a window for you on what is possible in terms of combustion science nowadays, so the state of the art of the numerical combustion in general. Because these things may appear a little too theoretical, but really, let me stress the fact that the jump between this stuff here that we're doing now and really the more sort of application-oriented stuff that you can do with computing is really very short. It's a very small step. What is hard in this topic is really to give you the foundation, okay, the basic foundation of and the notions of what's behind the physics of combustion. Okay, so I wouldn't want it to be a little bit too theoretical, but it is. I mean, unfortunately, we can't really avoid it. Can you see the whiteboard correctly? Are we?
Sí.
Are we recording? Yes.
Sí.
Fine. Okay, so we saw linear systems. Okay, now we're going to abandon linear systems. We've said too much even about them, but why did we do them? Because we really needed a blueprint, okay, a backdrop, a background on which to develop some notions or some, at least, initial theory on nonlinear systems. So I can actually draw, like make a parallel here between linear systems and nonlinear systems, okay? Really the source of complexity that you will find in engineering and in general, in all aspects of science is most of the times really this dichotomy here between linear and nonlinear systems. Actually, let me get rid of these headphones. Can you still hear me? Because last time you can hear me, right?
Sí, Dante.
Okay. So the linear systems, so linear ordinary differential equations, right? They're in this form, okay? Well, let's put it over here, the dot, okay? With a constant coefficient matrix, okay, it's an initial value problem in the sense that we have an initial condition. So it's an initial point in your phase space, and then essentially the solution is the trajectory, okay? X, gosh, that's supposed to be an X of t, which, by the way, has an analytical expression. So this is a phase flow, which is the operator, okay, the matrix exponential that maps the initial condition, okay, into the solution at time t, okay. So there's an analytical phase flow. The equilibrium point is unique, and it's identically equal to 0, the origin, okay? And what else did we see? Well, we saw that there are stable and unstable eigenspaces, okay? That are very special in the sense that they are invariant for the dynamics. If you start within one of those eigenspaces, you will stay imprisoned, let's say, in that eigenspace for every time, for all times, okay? So no matter how much you integrate, you will stay in that sort of subspace. the very important aspect of linear systems is that these extend throughout the phase space, so Rn, okay? And they're flat, right? They're not curved in any way, okay? So they uniquely identify the stability of the system. And in fact, the stability of the system, or if you will, of the equilibrium point, okay? Clearly these subspaces will extend from, okay, the equilibrium point, right? This stability is valid throughout the phase space. So even infinitely far away from the equilibrium point. Okay, so that's really the let's say the incredibly simple and absolutely or infinitely simplified connotation that a linear system has with respect to nonlinear systems. Okay. The solution is analytical, okay, and so the invariant subspaces are flat, so they extend indefinitely throughout the phase space. Okay, so everything is known. Okay, even infinitely far away from the equilibrium point. Now let's see for a nonlinear system. Okay, and clearly within this category we have even kinetic systems, right? Okay, that we've seen. So chemical kinetic systems. So now you have a nonlinear function here, f of x, right, as a source term, as a right-hand side. This could be anything, but clearly it's not representable as a constant coefficient matrix times x. Okay. And again, it's an initial value problem, so we have the initial condition, okay, x0, something like that, okay? Now, what do we know about the solution? Almost nothing. We can formally represent it, okay? For example, in this case, like a formal operator, phi of t, okay, which maps, okay, the initial condition into the solution at times x. Do we know this? No. Okay, most of the time it doesn't exist. Okay, analytically, but formally we can write down something like this. Okay, now what's the equilibrium point? Well, it's not the origin, but we know that the equilibrium point satisfies this equation. Do you agree? So whenever the right-hand side, okay, is such that the f of x is such that it's equal to 0, then x is an equilibrium point because it's a stationary point, okay? The derivative is 0. Now, this is a nonlinear function, so how many solutions does it have? Well, it could have n solutions. So you have a multiplicity, okay, of equilibrium points. So x of equilibrium is not unique, okay? Now, another question that you may ask is, what are the invariant subspaces? Do they exist? Are they flat? Are they curved? What are they? How do I determine them? I'd like to stress the importance of this question, okay, because if we determine an equivalent form of the eigenspaces, okay, the invariant subspaces for linear systems, also for our nonlinear system, then really we have opened a huge window, okay, on the dynamics of this system, and in particular on the asymptotic dynamics. Remember, we had the most unstable eigenspace dominating, right, at long times. Well, the same thing, or the slow subspace, okay, dominating at long times. Well, the same thing we'll be able to say here. Do we have, let's say, let's call them WS or WU as the invariant subspaces or invariant manifolds associated to this system. Of course, how many do we have? Well, we have, of course, more than two. I'm just writing down the two categories that you may have. Okay, one may be stable, the other one may be unstable. So, how do we proceed? Well, I won't bother you too much, okay, with the theory. So let's now close this thing here, because we're going to be talking about now nonlinear systems. Well, a good starting point is, for example, this thing here, the Hartman-Grossman theorem. Okay. Do we need to know this? No, I'm just going to just give you the outline of it, just to tell you that, just to open a little window on dynamical system theory. Just to tell you that, in fact, these invariant subspaces actually exist. Okay. Now let's see in what form they exist. So suppose you have your nonlinear system. Okay, sorry, I tried, but I failed. So your nonlinear system, okay, and suppose that you have an equilibrium point, okay. And concentrate on in the vicinity of the equilibrium point. Okay, so let's try and concentrate on a close sort of neighborhood of the equilibrium point. So what can we do? Well, we can define a distance, for example, a vector distance between, for example, any point x and the equilibrium point. Okay, where in some norm this distance is small. Okay, so we're in the vicinity of this system. Okay, now is there any way we can define a some sort of linearized form of the original linear system? Okay. Well, let's start from our nonlinear system. Okay, I will do a very long story short, but suppose we linearize f of x in a neighborhood of the equilibrium point. Okay, what do we have here? Well, we're linearizing. Okay, so we're expanding sort of in a multidimensional Taylor series. We know that f of equilibrium is clearly zero by definition, okay? And then the other term will be a Jacobian matrix, okay, calculated at the equilibrium point, okay, times, well, that distance, psi, okay? What's the Jacobian matrix? Well, it's dfi by dx j, okay? This is a matrix sort of ij, okay? Which has the derivative of the ith component of f by the jth component of x, okay? And so if we've linearized f of x, then clearly we can rewrite in a vicinity of the equilibrium point x dot, which is equal to also psi dot, can be essentially expressed by sort of a Jacobian in the equilibrium point times psi. So you see that we have a constant coefficient matrix, sorry, a constant coefficient ordinary differential system of ordinary differential equations, which essentially characterizes the dynamics, okay, of small perturbances or small perturbations with respect to the equilibrium point, okay? So this is only in the vicinity of, in a neighborhood, okay, in a close neighborhood of the equilibrium point, okay? We have essentially our linearized version of the nonlinear system, okay? Now, what does the Hartmann-Grossman, let's call it a HG, okay? The HG theorem say, okay? So, suppose we have a nonlinear system, okay? And its equilibrium point, okay? And suppose that the equilibrium point is, well, there is a fancy word for it, hyperbolic. What does this mean? Very simply, it means that the Jacobian matrix, okay, calculated at the equilibrium point does not, okay, have eigenvalues equal to 0. So essentially, always suppose that they're real and they're either positive or negative. Exactly like we did before with the linear systems, okay? So we have stable and unstable eigenspaces, okay, emerging from the equilibrium point. That's all, okay? So if this equilibrium point is hyperbolic, look, there exists. So if x of equilibrium is hyperbolic, okay, we can say for sure, and this is what the theorem says, that we have some localized version, okay? We can call it WS, okay? Localized version of stable and unstable invariant manifolds, okay? We just let me put local because clearly this Hartmann-Grossman theorem is only valid locally, okay? Locally in the vicinity of x of equilibrium, okay? So I will draw a diagram later on. This will be very clear, okay? So there actually exists. So we can say, there are invariant manifolds for the nonlinear systems, okay? For the nonlinear system. So we've actually answered positively to our original question. Yes, we do have invariant manifolds, and they are, let's say, topologically equivalent. Sometimes you can use the word conjugate, and I'll tell you what it is. To, okay, the eigenspaces, okay, which we call ES and EU of the linearized systems, which is x dot j of x of equilibrium psi, okay? So long story short, you take the nonlinear system, okay? You linearize it, you have this form, constant coefficient system of ODEs, This system of ODEs features this matrix here, which is the Jacobian calculated at the equilibrium point. You calculate the eigenvectors, which represent stable and unstable manifolds, for example, just as we saw yesterday, okay, for a linear system. And now I can say, wait a minute, for the nonlinear system, okay, there are these two that belong to these, so these two invariant manifolds or invariant subspaces, they emerge from the equilibrium point and they're topologically conjugate to ES and EU. What does that mean? Topologically conjugate, it means they're tangent and they have exactly the same dimension. So, suppose you have the equilibrium point. You will have, now clearly I'm going to have to make a straight line, which I can't do. So this is your equilibrium point of the nonlinear system, okay? Now you linearize the system, you will have then this matrix here, the Jacobian, calculated in the equilibrium point, okay? And this will have an unstable, for example, EU and a stable eigenspace. So we can write down some arrows, so pointing away from the equilibrium point in the unstable, pointing towards the equilibrium point for the stable one. Now, what about the nonlinear system, these two? Well, they will be tangent, okay, and have, I'll try, okay, and have the same dimension. So the stable one will be very close here. You see? I'm pointing here, okay. Will be tangent to ES, okay, and will have the same dimension. Okay, same thing for the unstable one. Oops, sorry. That's supposed to be tangent, okay? Sorry, that's not E. That's W. U, okay? So again, these we can write down some arrows. You can draw some arrows. So this is unstable. So the direction will be away. Okay. They're of course invariant directions. Okay. So if you start from here, okay, the trajectory will stay. Okay. On WU, because clearly it's an invariant subspace, and well we can write, we can also, okay, and then for the stable one we'll have these arrows clearly pointing towards the equilibrium point, and so we can complete any trajectory, because now the trajectories will go this way, they will go this way. Okay, very similarly to what we have seen for the linear system. Okay, but you see they're curved. These invariant manifolds WS and WU are curved. Now, of course, I could do exactly the same thing with the slow and fast. Okay. So, for example, if you have the stable eigenspace stable fast, okay, it's associated to the very negative, okay, so the most negative, or the most stable eigenvalue. And then you have the slow one. Again, okay, we're going to have an equilibrium point. Okay, from here, you're going to have, okay, something like WS slow, okay, of the nonlinear system. Okay, you can complete this picture here. And so, and then you have tangent here, okay. Fast, okay. So all the trajectories will go like this and will be attracted towards the slow manifold, or the slow, okay, and then it will go to the equilibrium point. Now, what's the use of this? Well, it's very useful. First of all, again, this is only valid very close to the equilibrium point, okay? What happens away from the equilibrium point? So you have an equilibrium point here. You may have the invariant subspace, ES, for example, of the linearized system passing through here. Again, as we saw right now, you can have a tangent, okay, local invariant manifold, which is stable, okay, in the vicinity of the equilibrium point. Now, what happens if I go farther away? Well, it could do all sorts of things, okay? It could even go like this. So you see, the Hartmann-Grossman theorem is only valid in the vicinity here, okay? So you have to zoom in, okay? You have to zoom in very close, okay? So this would be, so you see, this would be WS. Local is only here. But the actual WS, okay, is something that could be completely folded. Okay, for example, in this case, what you have here, you have another equilibrium point, and this is called a homoclinic orbit. Okay, so you see now that for a nonlinear system, the stability is really complicated, because now it does not extend infinitely throughout the phase space, okay? But it's only something that is local, okay? Here. So it's pretty complicated. And this is, by the way, as far as we will go, okay? In terms of the description of this. Now, why are we interested in the Hartmann-Grossman theorem? Why are we interested in invariant manifolds? Well, if we can determine the slow invariant manifold, we write it like this, of the nonlinear system, nonlinear system. Well, what do we know? Well, by construction, okay, from linear systems, we know that the slow manifold, okay, so if we have a system where all of the eigenvalues, for example, of the linearized systems are negative, it means that locally all trajectories will go to that equilibrium point, right? There is no saddle, there is no shooting to infinity. Everything will collapse to an equilibrium point. For example, a thermodynamic equilibrium, okay? We also know that the asymptotic behavior of this system, of this dynamical system, okay, will be dominated by the most unstable of those stable modes. And in particular, the greatest eigenvalue, okay? And this will be associated to the slow invariant manifold. And so the asymptotic dynamics of my nonlinear system is something like this. X dot equals f of x, okay? We can call it constrained here, okay, to the slow manifold, okay? And by the way, because it's constrained on the slow manifold, it will be sort of a lower dimensionality, so it will be simpler, and it will be non-stiff. Why? Because now there's only the slow timescales active. Okay, all of the fast timescales are essentially exhausted because they've already been expressed. Okay, we are already on the slow manifold. We have already been attracted by the slow manifold. Okay, the whole point here of so-called reduction methods, okay, or simplification methods, or let's call them reduction methods, is in fact this: we search, okay, for WS slow. So the stable slow manifold, or the slow invariant manifold, okay? So it's slow, meaning that it's characterized by the most unstable of all the stable timescales, okay? And so the less negative, okay? And it's invariant because if the dynamics starts from this graph, essentially, okay, it's a curve in the phase space, it will stay in that curve, okay? And so you have, if we have a way of finding this, then if we compare the nonlinear system, which is generally stiff, okay, that is, it's characterized by many timescales and they're very far apart, one from the other. It's generally high dimensional. Okay, why? Well, because imagine a chemical system composed of 1,000 or 100 species, it's 100 dimensional. Okay? And the reduced, okay, counterpart will be what we wrote before. So x dot of x, with that, where the dynamics now is constrained on the slow manifold. But of course, we need to know it. Okay? And now this is non-stiff. So it's characterized only by the slow evolution, the slow timescales, and it's generally lower dimensional. Okay? So all of these techniques generally have one and one only goal: to find this for a nonlinear system. Okay? Now, can we do this easily? No. Okay? There is no easy way of finding the slow manifold for a nonlinear system. However, what we can do is we can find them, in fact, not just the slow manifold, but also the fast manifold, okay, or the fast fibers, as we call them, when you can write the system, the nonlinear system, in singularly perturbed form. Okay, so we saw this at the end of not last lesson, but the one before. Okay, so usually you cannot find them. Okay, because it's a very high sort of dimensional system. It's very complex, and so are the slow manifolds. Okay, the slow manifold. But a situation where in which they can sort of be treated and they can be determined is when the system can be rewritten. So if the original system, nonlinear system, can be rewritten in singularly perturbed form. Okay? Then, if we can do that by non-dimensionalizing the system appropriately, we can sort of extract a fast and slow time scale, and we can sort of have a very small number appear, epsilon, remember? And then by just letting epsilon to 0, what we can do is we can shrink to 0 the fast time scales. Okay, we can make them instantaneous, and as a result, we can just reduce the system, okay, to only its slow time scales. And if we can do that, we can also find at least an approximation of the slow manifold, the slow invariant manifold. What do we mean by a singular perturbed form? Well, we already saw it. So let me just rewrite it. So we start from our original implicit form, let's say, of the nonlinear system. If we can somehow manipulate this and rewrite it in the following singularly perturbed form, then we're good to go. So what we do is we split X, okay? Into a subset of slow and fast variables. So we split it essentially in two sets of ordinary differential equations. Okay? One for the slow and one for the fast evolving species or variables. Okay? So in this case, we will have, for example, g of s, which is a function of x of s, x of f, okay? And generally speaking, a small number epsilon, okay? On the other hand, for the fast variables, we have the form 1 over epsilon, and then another source term, g of f, g of s, g of f, and generally speaking, also an epsilon, okay? So clearly, if epsilon is very small, okay, we introduce a very small number epsilon, which, as we said, will be representative of the ratio of the fast, okay, to the slow time scales. And it's very small. So now, clearly, this equation here, okay, well, the rate of change is, suppose that g of s, okay, is order 1, okay? So we'll evolve on a time scale, for example, of order 1. On the other hand, in this particular case, we have a situation where we have a 1 over the small parameter epsilon, okay, 1 over epsilon, so epsilon is very small. So the rate of change, dx by dt, is very high. So it means that x of f changes very, very rapidly. And so x of f, the fast variables, will evolve on a time scale of order epsilon. That's why we split essentially the evolution in two systems, one for the slow variables and one for the fast variables. Okay? Okay, we have 5 minutes. So again, how does it work? Why is it useful? Well, again, let me stress the fact that this small number is representative. Of course, it will depend on the particular system, okay, that you're dealing with. It's generally speaking a very low dimensional system, okay, but it's a very useful technique to understand. So epsilon, depending on how you non-dimensionalize it and how you treat it, the number epsilon will have a physical meaning. Okay, it's a small number, but it has also a physical meaning, and it's the ratio of the fast to the slow time scales. So there will be some, in chemical kinetics, obviously there will be some reaction constants involved, of course, right? Because reaction constants are a measure of the time scale. Okay, so that's much less than 1. Okay, it's a very small number. Okay. So what happens if we place epsilon to 0? What are we doing? Well, essentially, what we're morally doing is we're taking the fast time scale and we're shrinking it to 0. Or if you will, we're taking the slow one and shrinking it or extending it to infinity. So what we're doing is we're taking one of the two time scales and we're making it much smaller than the other. So we're shrinking to 0 the temporal boundary layer that we saw before, okay, remember? And in doing so, we're actually doing something. We are highlighting, okay, let's write it here. The asymptotic behavior of the system. I hope you can see this because we're actually saying, okay, we're very far away from the initial transient. Okay, so who cares about it? Okay, we don't care. It's shrunk to 0. It's infinitely fast. What we care about is what happens later on, asymptotically. And if we write this, well, very, very simply, we take this epsilon, we can put it over here. Okay, and we have now a system that becomes essentially, it's essentially reduced because clearly now we have gs of x of s and x of f. Obviously now the parameter is epsilon is 0, and we have now that 0 is equal to g of f. So we have done a very dramatic, okay, transformation. We have transformed our initial system in a very dramatic way in the sense that now we've turned one of the two differential equations into an algebraic constraint. Let's write it here. Okay, this is still an evolution, and it's the slow evolution, oops, okay, of our dynamics. And now we have an algebraic constraint here. Well, it's an implicit function, right? This constraint is in the form of g of x of s, x of f equals to 0. So we can solve it, for example, for x of f as a function of, let's call it h0 of x of s. Okay, we can sort of solve it for the fast species. So you see now that whereas we are solving, okay, for our slow dynamics, let me just stop here for a second because I want to essentially add the other term. We're solving for the slow dynamics for x of s, but the fast dynamics is already known as a function of x of s because the fast dynamics will follow the slow manifold. This is an approximation h0 of the so-called slow manifold. So what we're going to write here is essentially h, instead of writing x of f, sorry, we're just going to write down the slow manifold here. Okay, so we have essentially reduced the system. Okay, so let me just write the final sort of step. We define essentially this slow manifold. In fact, it's actually called the reduced slow manifold. This is a theory which we owe to someone called Fennikel, okay, in the 1970s and 80s. And so essentially what M of 0 is this approximation of the slow invariant manifold. So we can write it down as the set of points such that essentially x of f is equal to h0 x of s. Okay? And it's not invariant in general because it's only an approximation. Okay? Okay, I will stop here. And of course, I mean, I'm not going to leave you like that. I'm going to make actual hands-on examples for this so that you can fully understand the power of this theory. Okay? Very good. Okay, I'll stop the recording here.